Now, we're studying the representation theory of the loop group, but in this kind of categorified sense, where we're replacing the loop group by some version of its algebra of functions, and we're looking at representations of this algebra of functions. And what we have been studying up till now this week, the geometric Langlands program, from this point of view, is the geometric Langlands program is a kind of global or automorphic aspect of this representation theory. So rather than studying just some random representations of the loop group, we're studying the representations that appear in terms of functions on the moduli space of bundles. And a lot of the motivations for the Langlands program are coming from the local picture, for just studying representation theory of Lie algebras and Lie groups, which comes from the local picture. And the global picture kind of suggests a lot of structure in this. And I should also say that this, comment again, that this is from the topological field theory point of view. What we're doing now, this kind of local geometric Langlands, which is the study of this representation theory of the loop group, has to do with this topological field theory, this n equals 4 super Yang-Mills on the circle, at least morally. I don't think we have the tools to make this statement precise either on the math side or on the physics side right now. But somehow morally what we're doing now is we're looking at these surfaces and we're thinking about what happens when we cut a surface along loops and try to glue it in terms of gluing data along the loops, which is now, the gluing data are now going to be representations of the loop group. But now we're at a high level of categoricity, so we're looking at these kind of loop group actions on categories. But OK, so this is sort of where we're at now, and now I'd like to talk about a specific setting where the first step after the spherical setting. So before we looked at the spherical or unramified story. Unramified story was given by, we described the Hecke algebra for loop group and LG plus was related to the category of representations of the Langlands dual group. In particular, it was a symmetric monoidal category. It was a commutative Hecke theory. So now we're going to go to the next step. So what's the next step? So the next step is called the tamely ramified story. So what's the tamely ramified story? I'm going to replace LG plus by a smaller subgroup. So let's introduce the Iwahori subgroup, which appeared in Ruminian stock yesterday. So the Iwahori subgroup is a subgroup of the loop group, defined by the property that, in fact, it's a subgroup of LG plus. LG plus has a map to G, which is evaluation at 0. So this is G of Taylor series. And we can take these Taylor series and evaluate them at 0. And we want to look at the subgroup of things which are upper triangular at 0. So the Iwahori subgroup are things that at z equals 0 are upper triangular. So this subgroup is kind of the analog of the Borel subgroup. From the point of view of Thier-Kac-Moody groups, this is the Borel subgroup of the loop group. So what can we do with this? Where we introduce the affine flag variety. So this is the analog of the affine Grassmannian for the Iwahori. So we look at LG mod I. This is the affine flag variety. And this has a geometry that's very, very similar to that of the affine Grassmannian. It's a union of finite dimensional orbits for the Iwahori group, which are the affine versions of Schubert cells. So these are all finite dimensional orbits, and what are they labeled by? They're labeled by an analog of the Bruhat decomposition. So the double cosets of a group by its Borel subgroup are given by the Weil group. So there's a similar statement here. The double cosets of the loop group by its Borel subgroup are given by the affine Weyl group. So this is the affine Weyl group, which you can write as a semi-Dirac product of the finite Weyl group, the Weyl group for G, with lattice. Okay, so this is our affine Weyl group. So now what can we do with this? Well, what did we do with the Grassmannian? We're going to look at some kind of algebra of functions on double cosets under convolution and try to describe this. So one thing we can try to do is first, again, to model this by replacing, so we can model, so what we're after is D modules on this space, so which is what we're going to call Hecke algebra. There's the Hecke algebra for the loop group and the Iwahori. We can model this by picking a finite field, by looking at functions on, we're going to look, instead of our loop group, we look at G now over FQ Laurent series Z, or we could put in here a p-adic field instead. We look at FQ Laurent series Z, and we take double cosets for the Iwahori subgroup of this, which is defined in the same way. So let's call this, so this is a convolution algebra of functions. Let me call it straight H, LG, I, Q. So one thing we could try to describe this algebra. This algebra is called the affine Hecke algebra. So what structure does this affine Hecke algebra have? So the first thing we can notice is that inside of this affine flag variety, we can put the finite dimensional flag variety. So inside of here, we just look at the orbit of the finite dimensional group G, and its intersection with I is Borel. So we have the finite flag variety here. So if you look at the functions on here, you're going to see inside of them the finite Hecke algebra. So this is going to contain the finite Hecke algebra, which is the algebra that appeared in the previous talk with G over FQ with Borel's over FQ. So this sits inside of this affine Hecke algebra. And in fact, this affine Hecke algebra is generated by this thing with just one additional generator, T0, one additional reflection. Yeah?
So when you say that you model this with the functions on this
right.
in the finite group, the finite field?
Yes.
So what do you mean?
So I just mean that I'd like to describe this. This is the object I'm trying to describe. And I'm, instead of doing this convolutional level of D modules, I'd like to have a different function theory, a function theory that I can calculate more concretely. And the way I can't do that complexly. If I look at, I don't have a nice measure theory on this loop group that I can easily deal with. But if I look at the group over the finite field, there's a nice hard measure theory. And I can do a convolution algebra of functions on this group, or on a p-adic group. And this is what is classically done in representation theory. And I can look at the subalgebra of some class of functions, on smooth functions on this group, which are bi-invariant and have convolution, under convolution product. So, and the idea is that that's going to be some model that's going to be closely related to the K group of this category. So if you want to get exactly this, it's a K group of this category with a little more decoration. So it's called mixed structure. But you can get exactly this algebra as some kind of K group for this. OK, so so the point is that this algebra is generated by just one more generator, and they still satisfy the exact same relations. So the Ti plus 1 and the Ti minus q equals 0, where I is now, in the SLN case, is now going from 0 to n rather than from 1 to n. And they satisfy braid relations. So this is a quotient of the group algebra of the affine braid group. So the affine braid group is defined just like the finite braid group, but with one extra generator, except that we don't impose this equation anymore. We just impose the braid relations for our T's. So the idea is that this Hecke algebra, LGI, is a categorical version. It has kind of generators, but let me not specify in what sense there, but it has objects, T sub I, that satisfy the relations of the affine braid group, but no longer this kind of equation. So in particular, this monoidal category, particularly it's not commutative, unlike the spherical case, and it's a kind of categorical version of the affine braid group. An action of this category, in particular, will give you an action of the affine braid group. So when we're looking at representation theory with tamely ramified representation theory, so whatever things this thing acts on, this is some geometric version of representations of the affine braid group. Okay. So now what we'd like to do is describe what this Hecke algebra should look like. And so how do we figure out so I'd like to give a Langlands dual description for this. So let me remind you that in the spherical case, the Hecke algebra of LG with LG plus was related to the space of, well, this was representations of the dual group, except for some extra derived structure that I've kind of been sweeping under the rug, and it'll become actually more clear in a few minutes. But I wanted to think of this as some kind of coherent sheaves. What is a representation of the dual group? I could think of a representation of a dual group as a vector space, in other words, a sheaf on a point with an action of the dual group. So this is the same as point mod G check. Oh, so a coherent sheaf on a point with G check symmetries just means a vector space with an action of G check. Okay, so now what's our Langlands dual description for the affine Hecke algebra, or this thing, maybe you should call this affine Hecke category. So first of all, what's our geometric space? We're going to look at where is this supposed to appear? So this thing appeared as the symmetries of the moduli space of, these were the symmetries of moduli spaces of connections on a G dual bundle on X at some particular point X, of X and X. And these were these operators, these representations of G dual gave us tensor product operators on coherent sheaves here. So where would we expect this tamely ramified thing to act? Well, we look at G bundles on, if we're going to look at G bundles on a Riemann surface X. So the Riemann surface right now is just auxiliary. I'm going to be looking at some local picture at this point. So I look at moduli space of, this is moduli space of parabolic G-check connections on X with respect to X, which means these are flat G-check connections with simple pole at X and a compatible flag. And a flag, so we have a flat G-check connection P, and we have a flag in the fiber of P at X, which is compatible with the connection, compatible with the residue of the connection, or preserved by the monodromy of the connection. So this is the space of Langlands parameters in the tamely ramified situation. We're going to take a point and look at connections that are allowed to have a singularity at this point, but we pick a little more structure. Then we pick a flag in the fiber at this point, which is preserved by the local monodromy. Okay. So this is supposed to be some kind of global picture, but I'm not interested right now in a global picture. I just want a local picture. What's the local data? The local data at a point X. Well, the local data that I get is something like, well, what do I have? I have a pair of a flag. So let me write this way. So I have pairs like this, where B is a flag. So this is the set of Borel subgroups of the dual group, and N is an element in the Lie algebra of B. So N is an element of the Lie algebra of the dual group, which is contained in B. So why is this the local data? So really the local data is this thing up to the action of G check, we're looking at our bundle. So we have a bundle on our surface. We have a point. We take the fiber of the bundle at that point. That looks like a copy of G. And we've picked a flag inside of it. A flag inside of it is a choice of a point in the flag variety. And so that's our local flag. And then, moreover, we have n, which is supposed to be the residue of my connection. I have a connection with simple pole, and I have a residue of my connection. And the condition is that this residue be preserve the flag, be upper triangular. So this is a kind of complicated way to say the cotangent bundle of the flag variety. So the cotangent bundle of G check mod B check. G check mod B check is the space of all flags in G. And well, I'm really looking at it maybe up to the action of G check. So the map from here where you forget n is just the description of the cotangent bundle. So the cotangent bundle of flag variety is flags plus nilpotents preserving it. So this is what other geometry we have here? We have the Springer resolution. So if we look at the cotangent bundle of the flag variety, we can just forget the flag, and we get a map to the Lie algebra. In fact, it lives in the cone of nilpotent elements in the Lie algebra. And this in fact, as Rubin described this as the moment map for the action of G check on this space. Okay, so now this is kind of my local. So the idea is that if I have a bundle with a connection and a singularity at a point, my local data is, well, I can forget that I chose a flag. Then a connection just has a residue. So the residue is an element here, and I'm going to look at connections where the residue happens to be nilpotent. So the residue lives in here, but it really only lives in here up to conjugation. If I didn't pick a trivialization of my bundle, I don't know exactly what the residue is, but just its orbit. And then I can also choose an extra structure of a compatible flag, and I get a point in cotangent bundle of a flag variety. So this is some geometric data describing, this is the local data of tamely ramified connection. And so now what we can ask is, what are the symmetries? What are the symmetries of this local data? So if we're trying to study modular space of connections with these parabolic structure, you can ask, what are the local symmetries of this space? So we're going to ask, what are the symmetries of these local data, which are points in T star. These are my local data here, but I wanted to preserve the map to the nilpotent elements into the Lie algebra. So I want something that acts on here, relative to this map. So so for this we introduce the Steinberg variety. So the Steinberg variety is, we take just the cotangent bundle of the flag variety, and we're going to look at kind of matrices that act on the cotangent bundle. So we can look at cotangent bundle cross the cotangent bundle. So functions on this would be some kind of matrices acting on functions on a cotangent bundle, but I'm going to look at the fiber product over n check. So I'm going to look at, so what does this mean? This means triples where I have n in the Lie algebra, which is nilpotent, and B1 and B2 are both flags, such that n is contained in both, in the intersection of the Lie algebras. N is contained in both. So that's this is my space, and so what do I mean by this is, the symmetries? I mean that if I look at functions on this space, so I'm going to look at Steinberg variety, and I look at coherent sheaves on this space, this carries, this is a kind of a matrix algebra. This is a family of matrix algebra over the nilpotent cone. So what do I mean by this? Remember that we explained that functions on x cross x have a convolution structure. They're just matrices, endomorphisms of functions on x. So here I'm going to take, so first of all, this is a matrix algebra that acts on just T star B check, preserving and check. So if I take a function on this product, and I take a function here, I can pull it up, multiply by my matrix, and sum up over the fiber and get a new function. So functions on here have a natural convolution structure, and they act on functions here, preserving them relative to this map. And the definition is just a definition of a matrix algebra. So this is a very simple convolution structure. It's much simpler than these general Heck algebras. It's just given by functions on a product. OK. All right. So in any case, this is some local geometric data. So this is and if you like, there's a little bit more structure, which is the space. The Steinberg variety carries an action of the group G check, and it carries an action of C star. So it carries an action of the group G check just by multiplication, and it carries the action of the group C star, which is rescaling my nilpotent element. So these are kind of the symmetries, rescaling the residue. So now we have so the theorem of Kazhdan and Lustig. This gives a description of the affine Heck algebra in these terms. So this is the Langlands dual description. So if you'd like, this is the tamely ramified version of the Satake theorem. So Satake theorem told us how to think of the spherical Heck algebra in terms of the Langlands dual group, in terms of representation of the Langlands dual group. Kazhdan and Lustig theorem tell us that the affine Heck algebra is isomorphic to the K group of coherent sheaves on Steinberg. So I'm going to look at, let me just emphasize, this is the K group of coherent sheaves, algebraic K group, which is equivariant with respect to these extra symmetries. And that this is an isomorphism of algebras. So the Heck algebra was an algebra by this convolution on double cosets. This is a kind of matrix algebra. So the idea, and if you'd like, if you put Q equals to 1, this becomes just the group algebra of the affine Weil group. You get rid of these funny relations. This becomes the group algebra of the affine Weil group, and that gives you just, you can forget about this C star. So if you're just willing to ignore C star, you're just looking at these kind of coherent functions on Steinberg, which are equivariant. OK. So why is this a kind of a local Langlands picture? Because this algebra will act on, if I look at my moduli, so why did I introduce all of this? If I look at my moduli space of connections with this parabolic structure, if I look at coherent sheaves on this space of these tamely ramified connections, this carries an action now of, well, of this Heck algebra. So this, wait, sorry, what's my notation? This carries an action of my D of Steinberg O. Why does it carry this action? Because my local data, I just look at my connection. I forget everything you want about the connection except what it does at this point. It has a flag, and it has a nilpotent element, which is its residue. And changing that is, you can act on that just by matrix multiplication by a function in here. So these are the local symmetries that act on the space of Langlands parameter. And Kazhdan and Lustig say that this is exactly the same as the symmetries that act on the other side, on the Iwahori side. So this theorem actually implied, this gave a proof of the Deligne-Langlands conjecture. Langlands conjecture, which is the tamely ramified version of the p-adic local Langlands conjecture. So the point is that this theorem tells you that this affine Heck algebra is really a family of matrix algebras over the nilpotent cone. And we know what representations of matrix algebras are. Representations of matrix algebras are easy, so that there's only one, basically, an irreducible one. So this tells you that if you want to understand representations of this affine Heck algebra, you can use this to describe it as a family of matrix algebras and then give a complete description of all the representations. OK. OK, so other questions?
What do you mean by by a family of matrix algebra?
Right. So I just mean that that this is well, what is a matrix algebra? A matrix algebra is something given by functions on a well, finite set, and I look at functions on z cross z, and I give a convolution on this just by matrix multiplication. So I look at z cross z, and I use the projection. So I take a matrix, take another matrix, and sum up over the middle factor. So that's how we define matrices. So now I'm just saying, suppose we have, suppose my finite set mapped to some other set. I can do a relative version of this. I can do a version of families, so a family of matrix algebras. And the point is that we know exactly what the representations of something like this are.
You just evaluated points.
Exactly. So the representations of this, there's basically only one representation of this, which is functions on z. That's that's the kind of the standard representation. And so this tells us that if you give some algebra as a family of matrix algebras, over the base, its representations are labeled just by points on the base. It's Morita equivalent to the base. So this tells me that representation. So the point, what I'm claiming is this is explained very nicely in the book by Chris and Ginsberg, that once you have this description, this really does work just that way. This algebra, the way we define its multiplication, there's nothing subtle involving group theory. It's really defined just by such a matrix multiplication. Therefore, its modules are exactly labeled by points of the base, roughly. So, I mean, you have to be a little subtle about this, but it essentially gives this picture does give, in a completely standard way, a full description of all the representations in terms of points of the base, which is this nilpotent cone.
Don't you also get reducibility? I mean, I don't think it should just be points on the base.
Right. No, there's extra.
It's subtly involving the fact that sometimes it's multiple sort of.
Right. I mean, there is extra data involving the fact. So first of all, you have the representations of G check. So you can localize this at any particular. This is a module over kg check of a point over the representation ring of G check. So that gives you an extra parameter. So these are the parameters, the S, N, and chi in the Langlands conjecture. But
this is a category of coherent algebraic sheaves.
Well, this is the K group. This is just the K group.
Of the category.
Yeah.
But you're saying that K group in particular is a vector space over the complex numbers. Are you saying that? Or do you have to complexify that? I mean, K groups usually are Abelian groups. They don't usually carry the structure of a vector space over.
Sure. No, I'm saying this isomorphic. Right. So I'm looking. Yeah.
Maybe it's isomorphic to an integral subalgebra, and then you have to complexify it or something. Is that right? Is it right what I'm saying?
I mean, this is going to be a. Sorry, I'm blanking here. Yeah. I'm not sure I see the problem, but.
I'm just saying that a K group is not usually a vector space over the complex number.
Right. Sorry. So this is right. So this is so what is this thing? This is a Z of Q Q inverse.
On both sides.
Yeah.
Okay.
Yeah.
All right. Okay.
This is a ZQ Q inverse module.
Fine. Okay. Good.
Okay. Sorry. Anyway, so I don't. Right. So the claim is. So I mean, it's of course an oversimplification to say matrix algebra. The claim is that this description, writing this algebra as just a convolution algebra from a product, there's a standard, completely standard procedure once you have that to give a complete list of all the representations. I mean, it's more subtle than just saying points on the base, but it's roughly that. You have to remember that you're looking at some equivalent K group rather than something else. So, so this is sort of the topic of the book of Chris and Ginsberg, and this is why one of the points of this Kirchstein-Lustig theorem that we now get a complete description of all representations of this affine Hecke algebra. Okay, so now what I'd like to mention next is it's a really remarkable theorem, which is due to Bezrukavnikov, which says the same thing on the level of categories. So what Bezrukavnikov does is he gives a version of the tamely ramified, but now geometric Satake theorem. So the geometric Satake theorem told us that we have a description not just of this K group, we actually had a description of the category of this Hecke category for LG and LG plus in terms of representation of the dual group. Bezrukavnikov's theorem says that if we look at the Hecke category, this affine Hecke category, it's equivalent to the derived category of equivariant coherent sheaves on the Steinberg variety as algebras. So in other words, with convolution. So there's a little adjective that I need to put up here that I don't want to explain. There's a notion of monodromic sheaves. So there's the same issue that I was ignoring in the first hour. There's a notion about how I think, what exactly kind of D module I look at, whether I allow some twisting or not. But if I'm willing to, let's not worry about that. We have, the theorem says that the same kind of picture is true on the level of derived categories. That the derived category of D modules, which are Iwahori equivariant, so D modules on these double cosets, is equivalent to the derived category of functions on Steinberg, which are equivariant for the group under the convolution, under this matrix algebra picture. So what this theorem gives me is it gives a complete description of the representation categories. Implicitly, it tells me that if I have an action of this on a category, it can be described in terms of the geometry of the nilpotent cone, in terms of the geometry of T-star flags mapping to the nilpotent cone, because this category is a kind of matrix category over this. In particular, it tells you that any module category over this somehow sheafifies. So H, L, G, I module categories, they all live over, which means they sheafify over T-star flags. So it gives a geometric characterization of these Hecke modules. So this theorem is sort of one of the more remarkable things in the geometric Langlands program. It's a lot more involved than what we have seen up till now. In particular, this is a isomorphism of monoidal categories which are no longer commutative. So this category is some version of the affine braid group. And we're describing this version of the affine braid group in terms of the geometry of coherent sheaves on this singular variety. So this theorem, there's a lot of applications of this result, and it relates to the modular representation theory that Rubinin explained. It relates to representation theory of quantum groups. It relates to representation theory of affine Lie algebras. It's been used to prove lots of conjectures of Lustig. And so it's a really remarkable result. I don't really have time to describe much of these consequences, but one thing that you can get out of this is maybe the least interesting thing of the many applications, is that you can use this to characterize precisely what the Taylor ramified geometric Langlands conjecture should be. This should tell you that if I'm looking at moduli space of G bundles on a Riemann surface, and I have with parabolic structure at a collection of points xi, if I look at D modules on this, well, then what we know is that at each of xi, we get an action on here of this Iwahori category, this affine braid group action for every point I. We also had the actions before of the Satake category, the spherical LG plus. And what this tells you, it tells you exactly that this category we now have kind of the spectrum. We know what to put in at the ramification points. So before we had a commutative algebra and we knew where its spectrum was. Its spectrum was a space of connections. And now at the parabolic points, we kind of know what the spectrum of this algebra is. This algebra is a matrix algebra over the flag variety, over T star of the flag variety. So this tells us that this space automatically lives over, sheafifies over the space of connections on the Riemann surface which have poles, simple poles at xi and parabolic structures. So it does not tell me that I have this equivalence, but it does tell me that one side kind of lives over the other side. One side naturally sheafifies over, and it enables me to make a conjecture that says that I have an equivalence of these categories compatible with the actions of the corresponding Hecke algebras. So this acts at every point xi by just changing the parabolic structure at that point. It's purely kind of pointwise operator. You just change the parabolic structure of the connection at this point. And these are these more complicated convolution operators. So this is the tamely ramified geometric Langlands conjecture. OK, so great. So we can make more conjectures. So maybe that's not so convincing. I want to point out that this theorem of Bezrukavnikov actually implies the tamely ramified geometric Langlands conjecture in a special setting. So if you, just like we pulled the trick when we passed from the Satake category to something global on P1, the same kind of thing, you can use Bezrukavnikov's theorem to prove, so this theorem actually implies the tamely ramified geometric Langlands in a very simple setting, perhaps, which is on P1 with tame ramification at the point 0 and infinity. So, so what's the point? If I look at this moduli space of G bundles on P1 with parabolic structure at 0 and infinity, this looks like the loop group. So what's my picture? I have P1, I have 0 and infinity. I'm going to describe this as a quotient of the loop group, but now I have a flag here and a flag here. So this looks like a loop group quotient by two Iwahori subgroups, kind of one that extends up and one that extends down, which is kind of combinatorially opposite to the picture we had before, which was LG mod I mod I. So let me now, and in fact, what is the space of connections? This is, so just to be concrete here, what is the space of parabolic bundles with connection here? It's something very simple. I give you what is a connection on P1 with poles at 0 and infinity? Well, it's given by a monodromy. That's why it's good to have these poles, otherwise it wouldn't be so interesting. So I have a monodromy, which is an element of the dual group, and I have parabolic structures at this point and this point, so I have two flags. You have a monodromy and you have two flags, and moreover, you have a compatibility condition. So here G is in the dual group, and B1 and B2 are in the flag variety for the dual group, and you have the condition that G is in both, that the monodromy preserves the flags at 0 and infinity. So this is the Steinberg variety, except we replace the Lie algebra by the Lie group. So but this space is kind of the group version, I'll just call it like this, it's a group version of the Steinberg variety. So the Steinberg variety, instead of thinking of it as a local parameter space, you can think of it as some global space. So this is kind of an analog where I put the G in the group, and I don't require it to be nilpotent or unipotent anymore. But the point is that, so let me state a proposition. So this is pretty easy once you have Bezrukavnikov's result. I guess I should, yeah. So this is kind of an easy consequence of Bezrukavnikov's result is that you actually can prove geometric Langlands on P1, P1, 0, infinity. This is equivalent to the derived category of connections, well, of this group-valued Steinberg. Compatible with Hecke actions. OK, so this one has to be slightly completed for the same reasons that appeared in Konstantin's talk. So even when you start writing geometric Langlands, in the simplest cases, you already find that it's not that there's some issues of one side tends to be a little bigger than the other. And this, you can either make some growth conditions like Konstantin suggested, or make some little completion here. So you have this this proposition, which is basically just taking Bezrukavnikov's result and kind of putting it on its side, just switching I plus and I minus. OK, so great. So you can actually prove some geometric Langlands statements in this kind of toy setting. So what is this good for? And so what I would like to explain is that the claim is that geometric Langlands in this very kind of local case, so we think of this as just a story about the loop group and its Iwahori subgroup, so you can think of it as a purely local story, or you can think of it as a global story on this very particular geometry, P1 with 2 points. I want to claim that this has a lot of relations to representation theory of finite dimensional real and complex Lie groups. So I'd like to try to apply this result. So this theorem of Ben-Zvi is going to be kind of the main tool, which we're going to try to apply now to get results about the representation theory of G itself. So how do we use this? So from everything I'm going to try to explain is work with David Nadler at Northwestern. We are going to try to link this kind of affine Hecke theory, this affine Hecke geometry, so the theory of Hecke of LG and I, with the kind of finite Hecke algebra, Hecke of GB. So before we saw in the representation theory of finite dimensional Lie algebras, you're interested in studying this version of the finite braid group, which acted in all the categories of representations. Acted on categories of representations of real Lie groups and category O in various versions. But now we have this really powerful tool that describes the representation theory of the kind of affine version of it. Representation theory of the affine braid group, we now know how to describe in some sense as some kind of matrix algebra. And the idea is to try to use that to get results about this algebra, which looks nothing like a matrix algebra. Okay. So what are the ingredients? So what are our ingredients? So there are two. Yes.
The red pen is not very visible.
Oh, okay. Yeah, I think the blacks are dying. So maybe they're, well, let's see. Oh, okay, great. Now it looks like I wrote my stuff in red. Okay. Yeah. So you can, on the tablet, you can just circle this and click a different color, but I won't do that. Okay. So what are the two ingredients? So there are two geometric ingredients that go into this story. One has to do with passage from the loop group to the group G. So we need to go from this picture, the affine story, to the finite story. And the way we want to do that is a version of S1 equivariant localization. So to say in one sentence, we have an action of the circle rotating the loop, and its fixed points are the group. So if you want to relate representation theory of loop group to the group, you should look at the circle and try to find a way to pass to fixed points. So that's one ingredient. The other ingredient is we want to pass from the complex group to a real group. And this is the harder one. How are we going to go from complex to real? And the idea is that there's a beautiful structure that this is one of the places where the Langlands point of view really helps you. There's the theory of base change, Langlands theory of automorphic base change, which is something you sort of don't have in this context. It's something you have in this loop group context. So one of the idea is going to be, I'm really going to kind of have some kind of picture where I go, if I want to understand how to pass from the loop group to the real group, I'm really going to pass from the loop group to some kind of real version of the loop group, and then by S1 localization to the group. There's some kind of picture like this that I'd like to explain. Okay. So, all right. So what's the idea? So first of all, for the S1 localization, let me just remind you of the usual story of equivariant localization in topology. Is if M is a manifold with a circle action, then I can calculate, so I have this S1 equivariant cohomology of M. So I can look at cohomology, S1 equivariant cohomology of M, which means I take cohomology of M and I quotient out by S1 in kind of a smart way. So I can do this homotopical quotient by S1. So maybe Borel construction. I don't know how many lines it's supposed to be, so let's keep it at that. But the cohomology of the quotient is a module over cohomology, S1 equivariant cohomology of a point, which is the cohomology of the classifying space, which is CP infinity, and so polynomials over some generator U in degree 2. Okay, so to a space, I can look at its equivariant cohomology, and it's a module over this polynomial ring. And the kind of equivariant localization story says that if I look at the localized cohomology, which means I tensor S1, the cohomology with C of UU inverse. So if I invert this generator in degree 2, that this localized cohomology is captured by, this agrees with cohomology of the fixed points. So this is captured by the cohomology just of the fixed points of M. Well, with appropriate coefficients. But the point is that you can pass from a space to its fixed points on the level of cohomology by first looking at not ordinary cohomology, but equivariant cohomology, and then you do some periodicizing. You invert this generator in degree 2. So at least in the Z mod 2 graded vector space, you get the Z mod 2 graded cohomology of the fixed points from this picture. Okay. So now, how does this apply in our context? We're going to try to apply this to the loop space. So this is a technique with a long history, and trying to apply to the loop space, and you always have to be a little careful because it doesn't really apply directly in the case of a loop space. But in any case, the idea is we're going to try to study loop spaces. Loop spaces carry actions of S1, and the fixed points on loop spaces are the original space, Z. So you can try in various, try to use S1 equivariant localization to relate topology of LZ and topology of Z. This was done by Witten and Attia and many others since. So where are we going to do this? We're going to apply this to relate, roughly we'd like to apply this to relate the group algebra of the loop group and the group algebra of G. But I'd like to be more specific. I really am going to look at just at the Iwahori part. The technique is more general, but these are algebras that we understand. So one claim is that you can do the equivariant localization not just on equivariant cohomology, but on categories of D modules. So you can take this story of equivariant localization and you can lift it to the categorical world. And you can do it for categories of D modules. So let me state one version of this, which says that if you look at this derived category, and there's always some adjective floating around which is monodromic, which I've been ignoring. I'm looking at this derived category of LG mod I minus. So that's my Bun-G of P1 with 0 and infinity. So this is kind of the version of the Iwahori-Hecke algebra that we're using. You look at D modules on this space. And now I'm going to look at S1 equivariant D modules. And S1 is coming. You can think of it as rotating the loop, or you can think on P1. There's a symmetry of P1 fixing 0 and infinity. So I look at the S1 equivariant category, and I put a loc, or you could put periodic, which means I'm going to tensor this over polynomials in U with polynomials in U and U inverse. So there's a version of this on the level category. I can take this category, and it'll become, when I put S1, it becomes a module category of polynomials in U, and I invert U. And this claim is that the same localization theorem works, that you can look at, this is the same as D modules on the fixed points. Well, you'll have to tensor with polynomials and UU inverse. Now, but what are the fixed points? And the point is that the fixed points here are, well, you've just gotten rid of the L's. They're exactly B mod G mod B. So this side is our version of the Hecke algebra, of the affine Hecke algebra. This is a version of the finite Hecke algebra. Okay. So again, there's some adjective monodromic, but this tells you that you can pass from the loop picture to the finite picture by doing an S1 localization. Okay. All right, so this is not terribly surprising. This is a version of equivariant localization. But now what we'd like to do is pass to the other side of Langlands duality. So we have this, oh, it's even here. We have this theorem of Bezrukovnikov. And it tells us that this Hecke algebra relates to coherent sheaves on Steinberg. Now we know that we pass, if we do this S1 localization, we get from this to the finite Hecke algebra. So now you can ask what happens on this side. So formally, this is an equivalence of categories. So if you like, you get an action of S1 on here. So you can do the same formal categorical procedure and ask what happens. Now, or another way to think of that is we thought of Steinberg as some kind of space of connections on P1. And you can again think of rotating P1. So there's an S1 action. But it's a little funny because this is a finite dimensional complex algebraic variety, or mod G check. So it doesn't look like a loop space. This side really looks like some kind of a loop space. That's this thing. So the question is, what happens when you do this equivariant localization? What do you get here? Okay, so and this is where derived algebraic geometry comes to the rescue. So what you find is that okay, so in fact, the Steinberg variety, this nice finite dimensional variety, mod G check, it is in fact a loop space. It's a loop space. Another word for this is called inertia stack. It's a loop space in the sense of derived algebraic geometry. So maybe I won't try to explain derived algebraic geometry in the next 2 minutes. But the idea is that in derived algebraic geometry, we have a version of a loop, a circle, which is given by, this is really a simplicial set. There's a version of S1 which has nothing, this loop space has nothing to do with maps from C star into Steinberg. You start calculating maps from C star to Steinberg, looks nothing like, C star into, well, this doesn't look like maps from C star into anything. But there's a version of the circle which is a purely homotopical version, and that lives in this world of derived algebraic geometry, and you can look at maps from this purely homotopical S1 into something, and the thing is, you ask, what is that something? And that something ends up being exactly the flag variety of the dual group. So what you find is that the Steinberg variety is in fact a loop space, and it's a loop space of the finite dimensional flag variety. So I'd be very glad to explain later what these loop spaces are, what they mean. The word, if you've seen inertia stacks, this is basically what a loop space is. So it basically means that the loop is only going through the automorphisms of points. The loop doesn't have time to move around the space. It's a very fast loop, so it sort of just wraps around automorphism of a point. It's kind of a beta to think of as a zip line. Maybe I should point out that for X, a smooth scheme, the loop space in this sense, Lx, which is this simplicial maps from S1 to X, is just given by the tangent bundle of X as a supermanifold. It's just the odd tangent bundle of X. So this is something very familiar from physics, studying quantum mechanics on a space that, or sigma model on a space, that the odd tangent bundle of X appears as a kind of loop space. Okay, so since I'm running out of time, let me just proceed to say, well, okay, it turns out you can think of Steinberg as a loop space. And in fact, it's a loop space of something very nice. It's a loop space of flags mod B. So then you can ask, what does that equivariant localization tell you? You have a loop space. It has an action of rotation of the loop. So you can ask, what happens when you do a rotation of the loop? And something kind of cool happens because of this in this derived picture, that the loop space has something to do with odd tangent bundles. And odd tangent bundles have, the odd tangent bundle of a space is something that carries a canonical odd vector field called the de Rham differential. So the de Rham differential can be thought of as an odd vector field on the odd tangent bundle of a space. So this tells us that this loop space of varieties have something to do with de Rham cohomology. This is also a version of what, this is a very familiar to people who study cyclic homology, that cyclic homology is a category of coherent sheaves on its loop space, or at least on small loops. So this is a small loop space. And you take the S1 localization, this is the same as D modules on X. I guess, again, tensor to CFU inverse. So something funny happens here is that when you do these loop spaces in this funny derived world, when you do localization, you go from coherent sheaves, from O modules to D modules. That's just because you're going from functions to de Rham cohomology. That just means you're looking, S1 equivariant just means equivariant for the de Rham vector field. In other words, flat connections. Okay, so that's the story. So what do we get? We get the following picture, that this derived category of Ben-Zvi P1, well, I guess it's over here. So, well, okay. 0, infinity, D. This is equivalent by Bezrukhamnikov to Steinberg O. So I guess I should. Then you pass to S1 equivariant localization, and you get exactly this category of so we're going to HG check, and here we get HG check B check. So as a result, you get an equivalent of these two sides. So here it's some monodromic version. Here it's a non-monodromic version. So as a result, you get a theorem which gives you a canonical equivalence as monodal categories between the kind of finite Hecke category for G and the finite Hecke category for G dual. Because this is exactly D modules on flags mod B. So that's what's produced for us by this equivariant localization. So this result, this is actually a strong form of Sorgel's conjecture for complex groups. So Sorgel proved his conjecture in the case of a complex Lie group, and this is a slightly he gave an equivalence between these two sides, but he didn't have a canonical characterization of it. So this gives a kind of a canonical version of the Sorgel conjecture for the case of complex groups. So if you like this category here, this is the category of Harish-Chandra modules for the complex Lie group. This is a category of infinite dimensional representations of this group. And so we're saying that this category of infinite dimensional representations with its braid group action is equivalent to, has a kind of Langlands dual description. Okay. And right. And in next week's series of talks, I will explain how to say. So let me just say 2 words, and I will stop. And so 2 words. So how to go from. So now, of course, the most interesting part is how to go from complex groups to real groups. And the point is that there's this picture of base change. And automorphic base change says that if you're on the world of, if you have a covering space of curves, if you have a covering space of two curves, gamma is here supposed to be the group, so y is a quotient of, so these are both algebraic curves. We can describe connections, G dual connections on X as G dual connections on Y, which are gamma equivariant. This is sort of something tautological. We can describe connections on X in terms of connection on Y. And you can formulate this in terms of Hecke theory. You can say that I can describe O modules, the category of O modules on this thing, in terms of categories O module on this thing plus its Hecke action. So now the Langlands philosophy tells you that a similar thing should hold on the Langlands dual side. If you knew the Langlands conjectures, it would automatically tell you how to pass between bun G of Y and bun G of X, how to describe D modules, bun G of X, in terms of D modules on bun G of Y. And so you can formulate that as a base change conjecture. And the claim is that we study this conjecture in a very special case where you look at, I guess, sort of a twisted case where you look at P1 maps to RP2. So what we're doing is we're looking at P1 with antipodal map as its real structure. And so we have, and this real structure will act non-trivially also on the group. So we have a group G, and we have an involution on it whose fixed points are the real group. And so you can construct a moduli geometric Langlands theory on RP2 for the real group. And so, of course, I'm out of time, but let me just say that we get out of these various results, for example, we get a theorem which is a real version of the Kazhdan-Lustig theorem. The Kazhdan-Lustig theorem that was up there before, which is a theorem describing the affine Hecke algebra in terms of Langlands dual data, which is, this theorem is an affine version of Vogan's character duality. So Vogan's Vogan's real local Langlands theorem, which described the K groups, we can get a version, in fact a loop version of his theorem, purely canonically using from this geometry. And we can also deduce Sorgel's conjecture if from base change, can prove that these base change in this very particular situation would imply Sorgel's conjecture. We don't know how to prove this general base change, but we do know how to prove it on the level of K groups. And we know how to prove it in some particular situations. So this gives us kind of a program of how to understand the real local Langlands conjecture by first doing the complex local Langlands, taking a base change and taking S1 localization. And I'm glad to keep discussing this with whoever has the energy afterwards. Thank you very much.